So we will learn about damped oscillations now. So till now we have dealt with rather free oscillations. Now free oscillations means, say there is a body, let's suppose this is a block, and a force similar to a spring force that only acts on the body. Now that means if you displace the body by x, then the spring force or the restoring force in free oscillations is kx only. So this is free oscillation. Now if you remember how we have derived the equation of free oscillations, then we will derive it in a different way now. We will derive it by the theory of complex numbers. You know complex number, so any complex number, say e to the power I theta, e to the power I theta can be expressed as cos theta plus I sin theta, right? And suppose this free oscillation, so m d2x dt2 equal to minus kx, that is the d2x dt2 equal to minus k by mx. Now for solving this we will assume a trial solution. Now for solving differential equations we solve with trial solution. Basically the derivation we are doing, it is not required for high school level physics, but still it is worth knowing. Say this is the trial solution, say x equal to b e to the power dt. Let's put this trial solution for solving this equation, differential equation of free oscillations. In the similar way we will deal with the damped oscillation. However, so if you put in this equation here the trial solution, then differentiate x once, what do you get? So x once dx dt equal to d b e to the power dt, and differentiate it again, you get d square b e to the power dt. Therefore if you put in this equation d square b e to the power dt, I will bring it to this side, plus k by m x in terms of so x we can also substitute like this, b e to the power dt, the trial solution is equal to 0. Now this reduces to an algebraic equation where this will cancel, b e to the power dt again e to the power dt. So what is the solution of d? So therefore d is equal to plus minus, see d square is a negative quantity, so d is plus minus I into root over of k by m. So there are two solutions. So the differential equation as the trial solution was x equal to b e to the power dt. So as we have solved for d, therefore x equal to b e to the power I root k by mt. This is one solution, and one more solution, let's write this as x1, one solution, and the second solution is b e to the power minus I root k by mt. Now obviously the solution will not be complex. I mean, if you solve for x, now x cannot be a complex number, it is a real oscillation happening, it should be a real number, but the solutions are complex. Now, by the principle of superposition, you know that if x1 and x2 are solutions, if x1 and x2 are solutions to the differential equation, then their sum x1 plus x2 is also a solution. Now here the solution has to be x1 plus x2. Why? Unless you will not get a real solution. See, now therefore the solution to this differential equation, here the solution will be obviously x equal to x1 plus x2. So, b e to the power I root k by mt plus b e to the power minus I root k by mt. So, therefore, x equal to, here the imaginary parts will cancel. So, you are left out with the solution as 2b cosine of root over k by mt. Now, this 2b is the maximum value of x. So, 2b is the amplitude that is A, and if this is a solution, you can add a phase plus phi also, that is quite obvious. So, this we have learned a way to solve for the differential equation. Now, we will apply, or we will assume a similar trial solution for solving the damped oscillation problem. Now, let us see what is a damped oscillation. See, usually suppose you have a spring mass system oscillating, say consider this vertical oscillation only of this spring mass system. So, will the oscillation carry on for long time? As we practically see that no, it will not carry on for long time. Why? Because if you displace it from x, now the unbalanced force is provided by spring force kx. Kx is the extra extension in the spring, I mean starting from the mean position. Now, so as it oscillates, here what happens? Due to viscosity of air, there is an opposing force, or that force is known as the damping force. So, for this type of situation where the damping force is viscous force in nature, it will depend on velocity of the body. It is directly proportional to velocity of the body. So, this here it is the damping force, B is the constant of proportionality. So, this is the damping force. So, in general we will deal with this type of damped vibration, where this will be the spring force, and as the displacement is given towards the right x, so the velocity is also towards the right, and the damping force will be opposite to the motion, that is BV, damping force. Now, let us write the equation. So, what you get? Mass into acceleration equal to minus kx minus bv, implies, can write it like this, m d2x dt2 plus bv means dx by dt plus kx is equal to 0. Now remember this k by m was square of the natural frequency. So omega naught square, where omega naught is the natural frequency. Natural frequency means the frequency of the free vibration. Okay. So just we'll write this equation again. M d2x dt2 plus b dx dt plus kx equal to 0 implies d2x dt2 plus b by m dx dt plus k by m x equal to 0 implies d2x dt2 plus b by m. See this, you can write here 2 and multiply it by 2. So you write here 2 gamma times dx by dt plus omega square multiplied by x is equal to 0. Here this gamma equal to b by 2m. This is known as the damping coefficient. Okay. Now let us assume a trial solution. So trial solution assumed for x is of the same form, x equal to b e to the power dt. Now let's put it here. Therefore, so if you differentiate it twice, what do you get? B d square e to the power dt plus 2 gamma b d e to the power dt plus omega naught square b e to the power dt is equal to 0, and some of the terms will go out. That is obviously b e to the power dt, e to the power dt, e to the power dt. Okay, so what we are left out with, d square plus 2 gamma times d plus omega naught square equal to 0. Now this is a quadratic equation in D. So the solution will be D equal to, therefore D equal to minus 2 gamma plus minus root over of minus 4 omega naught square divided by 2. So if you put it inside the bracket, that will be minus gamma plus minus root over of gamma square minus omega naught square. Okay, so therefore you have two solutions for x. x1 is b e to the power minus gamma t into e to the power this one gamma square minus omega naught square t. Achha. Next solution is x2 is b e to the power minus gamma t, again e to the power minus of omega naught square minus this one. Okay, now that's fine, but suppose this quantity inside the bracket is positive, then you won't get an oscillatory motion, right? So you will get an oscillatory motion when, for what situation? Motion is oscillatory if the thing inside the bracket is negative, that is this gamma square minus omega naught square is less than 0. So therefore we can also write the x1 as b e to the power minus gamma t. If this thing is negative, then you have to write it in this way: e to the power I root over of omega naught square minus gamma square t, and x2 will be b e to the power minus gamma t, again e to the power minus I omega naught square minus gamma square times t. Okay. So motion is oscillatory if this thing happens. If this quantity, this thing is true, the quantity inside the bracket is negative. So this case is known as under damped oscillation. Under damped. Under damped means the system will oscillate. Now this situation, now if this gamma square minus omega naught square is greater than 0, then the system is known as overdamped. Overdamped means it will not be oscillatory at all. It's an exponentially decaying function, and there may be this case at the borderline when gamma square minus omega naught square is equal to 0. Now this case is known as critically damped. Okay. Now for the under damped oscillation, if the oscillation is under damped, I should say that the oscillation happens only when it is under damped. So oscillatory motion means it should be under damped. So for the oscillation to happen, again, so this roots, so x1 equal to b e to the power minus gamma t e to the power I omega naught square minus gamma square t, and x2 is b e to the power minus gamma t e to the power minus I omega naught square minus gamma square into t. Therefore what will be the solution? Again the final solution for x has to be real. So that means you have to add these two solutions. It should be x1 plus x2. So that's 2b e to the power minus gamma t into cosine of root over omega naught square minus gamma square multiplied by t. Now this 2b, or you can write x equal to a naught e to the power minus gamma t cosine of root over of omega naught square minus gamma square multiplied by t. Now see, if you look at this equation, this term is known as the time varying amplitude. And this term goes for the fluctuation, variation, or say this term, this is also known as the envelope of the curve. Now I'll just show you how it looks like. So the equation was x equal to a naught e to the power minus gamma t cosine of root over of omega naught square minus gamma square multiplied by t, right. Yeah, that's it. It's time and this is x. Now So the amplitude dies out with time. So this one is the envelope of the curve, see this one. So this stands for the envelope of the curve and this stands for the fluctuation. That means what about this term? This is the angular frequency. So the time period, t equal to 2 pi by this much angular frequency, omega naught square minus gamma square. So that is actually this, no, any 2 points C in the same phase. So this point and this point, this is the time period of the damped oscillation. Okay.